folks, I'm big attendance, surprised. You guys don't know anything about RMS yet? Oh, it's a story. Well, I have 5 hours worth of slides here, so I'll go through them, slow me down, or speed me up as we see fit. The main angle for this was really for those people that have not designed their own application, have not, were just given a VMS system. Where do I start? I don't know. I have no clue what RMS is doing. I have this COBOL program, and it finds records in files, apparently, hopefully. And it's no longer fast enough, typically. So it sort of works, but not fast enough anymore, mostly because of scaling, right? You get more volume to deal with. And what can you do? What must you do? Is the performance adequate? And maybe don't touch it. And there's quite a few angles where that would be the case. Shall we go and learn RMS in a hurry? Are you going to finally go to that course or something? And then maybe check this presentation for some general tips and a couple of details. We'll see how it goes. My topics: credentials, set RMS, buffers and locks we'll talk about the best we can. FDL, of course, will be talked about. Questions throughout if you feel like it. I'll try to repeat them. Silly slide maybe, but my RMS credentials is that I've been doing it for 50 years, 45. And starting in the Netherlands with some basic programming, so international support from Heuvel, and then we got recruited to VMS engineering and went sideways, and now I'm kind of back. So I'm back and touched the RMS code again, surprisingly. But my biggest question is, what are your RMS credentials? You know, if this was an Oracle, Snowflake, SQL Server application, would you have been allowed to touch or manage this application without being a certified Oracle engineer? Probably not, right? You have to be, you wouldn't be hired, you wouldn't be in the process without being certified, having gone through training sessions, or at least managed to answer the questions correctly. And, you know, you would have teams and different layers of developers and maintenance people. And now you're just there on your own, and you never had any RMS training, and you're managing the corporate jewels. How does that work? It shouldn't be that way, but that's actively how it is. Best we can offer you is a bunch of manuals, but the manuals are not training sessions. You know that. There's reference information. If you know what you're looking for, it's there and explained, but you didn't know what you were looking for. I like to emphasize that experiment, because there is, in hours, not weeks, you could learn an awful lot about RMS, and this would just be convert a file in your play area, dump 6 records, dump 12 blocks, and see what's in there. It wouldn't take all that much to RMS is a simple product in itself, and you can learn, you can teach yourself by just checking it out with regular tools. Now, if you then are tasked to maintain your RMS files, then this is one of the cases where close enough typically is good enough. There's no point in trying to get the last 2% out of there. You want that 50% and declare victory, right? You want it twice as fast, declare victory. To go 10% faster, who cares? It's fine. Buy a bigger box, so to speak. And what we're going down to is, of course, that 80-20 rule. We have to, there's a small area in your application that has a large impact on your performance. The trick is to find that small area and focus your tuning there. Any tuning better than none? Yes, these are the simple things, like just make file extents be 2000 blocks for everybody all the time, anywhere. Make RMS buffers be 50 buffers no matter what, because we used to have only 2 buffers or 3 buffers because memory was expensive, right? Not anymore. My simple rules is, so one of those simple rules is every active file shall be converted once a year, whether it needs it or not, because you don't know whether it's going to help. But if a file hasn't been converted in a year, it's about time you did it, because you want to make sure that all the records are readable, for example, right? And maybe it actually speeds up your processing. Who knows? The bigger angle is performance for the talk, but also resilience, and make sure the data is there and can be seen. No bucket size shall be less than 8 or larger than 32. I'm going to talk about buckets a lot. RMS originally said, how can I get my work done with the minimum amount of memory? We're talking 1975, 1978. How can I get my work done with the minimum amount of memory in the least space needed? So if I need to make a collection of data records and I'm going to stick them in a bucket, I'm just going to make the bucket big enough to hold that record. Done. That's not how you get performance. You want a big bucket full of records, right? So if you don't know and you see a bucket size of 1, 2, 3, bump it to 8 and hope it gets better, right? But for some applications, a bucket size of 2 is just perfect and makes a difference. So then you have a reason for that. So it's fine if you take a small bucket size or the maximum bucket size 63, but please explain to me why that's the right decision at that point. If you don't know why, then just pick this average number. No index shall be deeper than 3 unless you have a good reason for that. Simple tuning is again that file extent should be if a file needs to grow, make it grow really 25% of the file. You want it to grow only once and not over and over and over, nickel and dime your data. Unfortunately, the RMS file system maximum is 65K blocks, so we sort of limited here. So we better have to pre-allocate. From my perspective, don't worry about cluster size. And on the next talk, I'll tell you why you would worry about cluster size, but that's you have to keep that separate. Here I'm telling you, don't worry about cluster size. Because bucket size, we're talking index file, bucket size defines the performance. Compression, folks still worried a little bit about compression. Compression is a good thing. Compression saves CPU, believe it or not. And so compression, use it, and you should try to learn what your files are all about a little bit. Is this a driver or is this a slave file? Are we doing 5 updates a day and 5 million reads, or the other way around? You should know a little bit about how your files work, and that's visiting customers. All too often if you ask them how are you using the system, there's this one guy in the corner that knows how is responsible for the file. And if he's on vacation, too bad. Now that was for maintaining the files. And then what I miss often is rules for designing a file. If you're going to design a file, you should make the extra effort. You should get it close, because you only do it once. There's no going back. Nobody will typically don't dare touching it anymore. They don't even dare touching a bucket size, which is just an artificial clump of records. There's no application dependency of how many records you fit in a bucket. It should be completely transparent, but there's quite a few customers that say, no, it works, don't touch it, don't you, right? So if you are designing a fresh usage of a file, then we need to try to avoid the need for frequent converts. So if you, and we'll talk about that a little bit more, if you add records in an ever-increasing sequence, then they will be nicely stacked, and there's no immediate reason to convert your files over and over. If you fill up your files randomly all over the place, room has to be made, bucket splits will happen, and converts are required. Which means that you might even need an artificial key, which is 1978. Nobody knew about universal IDs or anything like that, right? And giving artificial keys to value. But nowadays, you might actually choose an ever-increasing number for your records and have the your normal social security number, last name as an alternate key sequence. Now you avoid your converts because records will be added over time. Duplicate keys can be a point of contention in RMS files. We'll get to that. That doesn't mean you cannot have them at all. Some level of key duplication is just fine. Hopefully we'll get to that. And please help the future support people for the product and say, I do need this file to be converted once a month. I do need its size to be allocated based on your business changes, right? So now I want to go into a very detailed subject, and I do not know the level of interest in this. How do RMS index files even work? Is there a level of interest in that? Yeah, I see several now. So I'll take some extra time on these slides, which means I'll have to drop some slides on the back end. So the definitions. A bucket is the main internal storage unit. So we store our records, and we store our data records and our index records in buckets of data. The bucket is bucket size. This is FDL term, right? If you design your files, you have this secret, this magic language, and bucket size is a word in there. This bucket size blocks big, and the bucket's identified by its starting VBN, the block number within the file. So a bucket 12 would start at block 12 and could run into block 16 or however long it's going to be. Then the buckets are going to hold the records. The records are ordered by primary key within the bucket. That's how RMS is designed. Within the bucket, records will be ordered by primary key. And that's already leading to bucket splits and where you're going to split records eventually. Each record gets a new ever-increasing ID within the bucket. So you add a record that should belong in this bucket, because a bucket is sort of assigned a key range, if you like. And so as we find our way to store a record, we get directed to a particular bucket, and we try to add it there, and we give it an ID range which will keep on increasing, but it is a 16-bit number, so you can and will run out for very specific applications. Normally, you put 12 records in a bucket and you move on to the next bucket, and the count starts over. But if you add, delete, you will run out of numbers, and we'll just put you in the next bucket, leaving an empty bucket. Then RFAs, and you'll see them in a picture momentarily. RFA is a record file address that uniquely identifies the record itself. So other file systems might use a primary key to say this is the record. RMS uses the RFA, a numeric address, block number, and that record number within the bucket number, and the record within that bucket. And that actually can get paid. You're allowed to remember that because it will stay there for life. There's only a few languages. BASIC is the only language that really grants support for RFA in the language right there. Other languages you can get there, but with more trouble. But the RFA, while it is a nice binary address to allocate that your application could use, is most importantly for those alternate keys, because we have files with not just a primary key, but also other ways of looking up by different columns, fields, whatever you want to call them. And the way you find the record back is not by primary key, but by the address, by the RFA. So RMS needs the RFA for that. And when we do split a bucket, when a record needs to be moved eventually because the storage ran out in the right location, we will move it to a new location and say, remember, I was record number 6,5, and where if anybody comes looking for 6,5, this is where you're going to go find me next. So it's one level of indirection. In a picture. Much better, right? Let me see if that works a little bit. Oh, that's too hard. if we look at an index file with a very simple set of records, and we loaded them deliberately slightly out of order, 1, 2, 6, 3, 7 is how we loaded the file in this case. So we're going to, as you create the file with nothing in there, RMS will give you a prologue, that's in block 1. It will give you an area and a primary key, which is also in block 1 for the primary key. And so there's a couple of overhead blocks before the first data bucket. The first data bucket has, and this is a little technical detail, so that first data bucket follows this overhead location, and so you cannot actually control its placement if you want to do the absolute fine-tuning of everything aligned on nice members. Anyway, overhead area, record is going to be loaded, a bucket is going to be allocated, and we're going to put the records in there. Bucket 1, 2, bucket full for the purpose of this demonstration. You don't want, normally you want more than 2 records in there. I'm going to load record number 3. I'm going to have 6, 7. So originally 7 would have been here, but now 6 needed to find a place in the right sequence. So we already have to split and make room for it. This, see if it's clear. Oh, the alternate, these were the primary key numbers, values, just numbers. Actually, let me get a show of hands. If you're designing a file with social security numbers, telephone numbers, and last name, which one is going to be the primary key? Social security number? Last name? Last name. Why? Because when is the last time you asked the question, give me the record with the next social security number? When is the last time you needed that query in an application? Ever? Never. When is the last time you said, find me Smith? That's not the right Smith. Find me the next Smith. That's a very common occurrence, right? So RMS has these data records in order. So all your Smiths will be in these 5 buckets. Social security numbers will be all over the place. Now, if you then need to go in quickly with the social security number, you say, because that's my main key. Well, not these days, you can't have that anymore. We'll have to go to the alternate key, but it's only 1 hop away to the data record. But that's a good price to pay every time versus being able to get 10 Smiths in one go. See where I'm coming from? So the alternate key, let's see, the traditional design, you will always find the number as a primary key. There's no doubt about it. So this is what you want and what you're going to get. What you're going to get is this. And then the alternate key might have a last name, and it will point to the right data record corresponding with that. Oh, sorry, too fast. Let's put some numbers on there. So the prologue, bucket 1, areas would be in bucket 2, primary key is in bucket 1, not bucket, in block 1 again. The first data bucket, depending on how many keys you have, would often be block 4. Then I have 1 block buckets here in this case. First records 4,1, 4,2, 8,1 was because of the 6 being ordered. So 6 came in first, right? Record 6 was put in the file before record with key number 3. So record number 6 with the key value 6 became record number 1 in bucket number 8. And 3 then became record number 2, because the main order is the key values, not the IDs. Okay. We jumped from 4 to 8. Why is that? Because as we filled in the file, we need an index to point to it. So the first index bucket would have been block 5 to point to my data record. All the data buckets are connected at the lowest level. So we can just keep on reading a file, reading forward through the file, which means that if any corruption were to happen in this space, we never have corrupted files, but A convert only needs to read the bottom layer and can easily overcome many issues that way. But we have a forward pointer in every file, in every bucket, and anything else I want to mention? No. So if we then look in the alternate key structure, the record for Mr. Bell has then the number 8,1, and we will know I'll have to go to bucket number 8 and pick record number 1 if somebody wants that record back. So this is how it's connected. And fine, this now exists. We've loaded our 5 records. File is there. Anything special happening in this picture right now? We're good with that, right? It's not rocket science. It's not rocket science. You can figure this out by following these pointers: analyze/RMS/interactive, down, up, over into the areas, down, whichever way you want to play that game. But now let's see where it's going to hurt a little bit. Let's now insert record with key value 4. So record with key, RMS goes into the system and says, all right, where do I find record? Where should it go? Well, it should go, let me find out where the primary key is located. Oh, the root of the primary key is here. I have a value 6, so my record with value 4 has to go, is before 6. This is the first record I have. It's less than 6 or less, so I follow this path down. The last record in the root is always key value FFFFF, just a large number represented by a star here. So we go down the index bucket, and the index now has 2 pointers again. 2, well, the value 4 is larger than 2, so that's not it. 6, yes, it's a legal place to go, so it follows the pointer under 6 to find the right data bucket to go to. We try to insert record number with key value 4, and there is no room for it. So now we have to split this bucket open, make room for it by moving some of the data to a different bucket. And that involves some work. All the buckets with all the elements with red surrounding it will have to be rewritten. Do we see that that's a painful process? So half your file is being updated because you added this one record in the wrong spot. It's not that bad. It happens all the time. This is the worst case situation. Normally, often it's just 2 more blocks, and you don't necessarily split up all the way up to the table. But this example shows how you would have to split up to the table. So now that record with key value 6 we've split 50-50. We tried to split 50. I forget whether we round down or round up. It don't matter really. So there was no room for record number 3, and we're going to move it to a new freshly allocated bucket. That key value 6 is going to be moved out. It remembers where it came from. It says I was initially created as 8,1, and therefore we create a little pointer here, an RRV data record. So we talk about 20 bytes or something like this. That says where if you were looking for a record with ID 1, because you remembered it, because it's in that alternate key structure where it is remembered, now you should find that as 15,1 over here. So also when you now come in via that alternate key, you have to take one indirection level. Now, this could become painful if subsequently that bucket is split and split and split. So what RMS decided to do, and I think it works well, is that if this resting place for the record with key value 6 gets split again, we know where it came from. We will then update that value here, say, I now live in 12,014. So we keep that one indirection level using those RRV pointers. Kind of nice, but if you split 500 records, you'll have to update 500 pointers, and they all moved over time. So 40 moved together to a new bucket, but 60 other ones have already moved to yet another bucket. So now you're multiplying IOs. it's okay. It doesn't hurt much, and there are counters to see how many bucket splits you have, and there's nothing much to do about it. But if you could have avoided it by just adding them at the end, you see that that would have been so much easier from the get-go to never have that split and never have that indirection level coming from the alternate key. Right, so one logical write, insert a record, turned into 5, 20 physical writes. And the other writes were, well, because I created a new bucket, the end pointer needed to point to the new end bucket. The area where we remember how much space we've used and what the next block is to use had to be updated. Those little things all come into play. Yeah, I talked about that. And so if we had, in the simplest case, if we just had added our record, if we previously added record with key value 4 causing the split, but if we add a record with key value 8, life is fine. We just move it in there. The index says high value. The high value didn't change. We don't even need to change the index bucket because it's still saying this is the last bucket in the file. So you can always find that. And index buckets don't change much because one index bucket should typically point to 20, 50 data records, right? So these indexes don't they multiply out very nicely typically. Eventually, room needs to be made, and of course, we special cases. If we add a new data record which wouldn't fit in the last bucket, we're not going to split that last bucket. We say, well, let's just add. If the key value is higher than the highest value in the last bucket, just add a bucket. Makes sense, right? So we don't need a bucket split in that particular case. We understand how RMS internally manages those records and finds them back, even if they moved. There's one painful area there that I don't like. If I could go back and, so to speak, I would add a flag saying no RFAs. Meaning if it's a single key only file, why would I on a bucket split try to remember all this stuff if nobody's ever going to follow the point of the remembered number? So that would be a nice flag. I think no RFAs. But single key files are fair. I'd say 50% of them are single key files. Lots of files have a bunch of keys, but single key files are still very important. That's the foundation, right? How that all works. Now, to make that's on the disk. To make that work in memory, and to make that work consistently in a cluster with concurrent access, we need buffers and locks. Now, what's a buffer then? A buffer is a chunk of RMS maintained memory. We use it to read a bucket into, and the default is local buffers only. So, which means a buffer is allocated to your process, and nobody else can use it after you read it because it's in your process only. RMS was designed conservative, and it's still conservative. We never changed that. So RMS is the default is. The number of buffers we allocate for a file is the deepest indexed at open time plus 2. Boo. Yeah, so if you create an empty file, you'll get 2 buffers. And if you then fill it over time, you have no room to play with. You have to toss one out to read the next and toss it out and read the next. XFC will be saying, oh, I'll bless you, son, and here's all your data. Anyway, you don't have to go to the disk. But the XFC is one level down, right? So if we can avoid stepping down, so much the better. So how many buffers do I then need? I do have a switch. I can do in my program. I can say allocate so many buffers. I think area contains in COBOL. I forget what it is, or there's all sorts of programming options. The simplest one is really set RMS/buffers equals 20 and be done with it, or 40 or 256 is your number, I think, right? No, we discussed that. So if we are just reading a record, looking up a record and saying and declaring done, one buffer is fine because we're never going to go back. Or if we do a get, one buffer is enough, because once we've read all the records from one bucket, we move over to the next and we'll never look back. Because we remember that case, again, back to those bucket splits and those retrieval vectors, we are in primary key order. So we will, when we read in primary key order, we don't need those jumps anywhere, ever. Right. So many buffers, we need many buffers to cache repeated operation. If we have a lookup file and we keep looking up different places, it would be grand to keep most of the index in place, that at least we don't need to read index buckets. We might have 1 million data buckets. That's not realistic potentially to cache those, but on top of the 1 million data buckets, there might be 1,000 index buckets, and we might be able to cache all of those. Why not? XFC will take care. If you don't do this correctly, XFC will make the IOs go away, but the work is still being done. And the problem with the XFC is the write shared file in a cluster. So if XFC build up a buffer cache for cache lines for a particular file, and somebody else on a different node opens the file for writes to the file, then all your data will be gone from the XFC, and you have to rebuild that. So XFC works great, but doesn't work in a shared update environment, which is fairly typical for RMS files. Out of the box, the defaults are just barely adequate. It just we kind of went over this. For sequential reads, we just need a couple of buffers. That'll be fine. Where do I set the local buffer count on in RMS terms? RMS has these internal. The languages make RMS disappear, right? You do an open, you do a read, a write, and a close. But behind the scene, open it really is an open and a connect, and the read is a $get call, and so on. So the $get call, the call that actually says RMS to create those, connect, will set up the buffers, and you can set them in a RAB, one of the programming interfaces. You can set them into an XAP if you want to go more than the RAB only has a byte field. The XAP has a word field for buffers. And in COBOL, you can say reserve so many areas, and each language has their own way of specifying that. But really, the simple way is set RMS, and that's perfect, but it does apply to all files at this point, which is probably what you want anyway, because you don't have the brain power to figure out the right number of buffers for all your files, right? How could you figure that out? Now, these were the local buffers, and you need those when you're doing your bucket splits and stuff like that no other process is interested in. But if I have if I have a large application, commercial application, I will have 50 processes or 500 processes all reading the same file. So what a shame would it be if they all needed to read the root index and the second level index and the third level index. So there's a concept of global buffers where RMS sets aside a big chunk of global memory, and it reads, in principle, it reads all the data into those global buffers. It can write from global buffers also. It can still use local buffers, but if it doesn't see any good reason not to, it will read the data into global buffers. It's really efficient in clusters because unlike the XFC cache, the RMS cache is protected by locks, and we will only have to flush out a bucket that was actively changed within the file by another node. Now we have to invalidate it. But if the lock sequence value box sequence number is still the same, it's still good, and we can concurrently read on multiple nodes. We don't broadcast changes, so it's quite efficient. We only say we have an inquiry. I need this bucket. Give me a lock on this bucket. What is the lock value block? Oh, it's the value I already have. I can use it. Oh no, it's a different value. I need to freshen up from disk. But we're not going to say every bucket that's changed, tell all the other nodes to make it go away, because they might never look at it anymore. So why waste time for that? So global buffers obviously need a big chunk of memory. That's the best way to use me. If you use global buffers, go big or go home or something like that. But once you have many users where we want to deploy that, they all need fewer local buffers to do their work because all the indexes are cached in the global buffer. So this is a silly calculations, but I could do 500 global buffers. That sounds like a lot of memory, but the alternative would have been 500 times 5 local buffers. So we would have 2,500 times a bucket in memory. So this is much more importantly, you don't need to read it again. RMS does not clone data from one process to the next. So the most important part is just that your data might already be there. Right, it's global buffers. Oh, I was cute on that slide. 15 more minutes. Yeah, almost done, right? So global buffers is the important part anyway. So the way to cache the index buckets and their alternate primary key, it's all fine. They sound like they're really important for reads. Of course, they're really important for reads. But if you write to a file, you still need to know where to write to the file. So you're going to read index buckets, you're going to read data buckets before you know where to write from. So they work in read-write applications. And then, if there's one thing I want you to take away from this meeting, if you're not using global buffers, okay, is there anybody not using global buffers yet? Do we all use global buffers for RMS files? I don't think so. I think there's quite a few people here that do not use global buffers because in 1987 somebody tried them and they didn't work back then, and we haven't tried them since. Well, I mean, they work. They really work. And very, very importantly, in version 7.3, and I hope you upgraded beyond 7.3 by now, we added Eleanor added a massive feature, and it's concurrent read locking in global buffers. So normally, when RMS needs to read a record, it will find out which bucket it lives in through the index. So because you remember the RFA, it will lock the bucket for everybody else, try to find the record, lock the record, and now it says I can throw away my bucket lock because I have my record lock. Well, if I now do a get next, let me get the bucket lock, let me find my next record, let me release my bucket lock. Kind of silly, right? So if we had only held on to that bucket lock, nothing would have happened. We could have just moved forward. And if Johan reads a record in the bucket and I read a record in the same bucket, why couldn't we be reading the same bucket at the same time, as long as nobody's changing it? So finally, in 7.3, concurrent read locking was made available by having some extra information next to the global buffers to indicate that a bucket is currently held in concurrent read mode. And yes, it's fine, you can keep on reading and you don't need to do a lock intervention. So what you heard just now is that if you do a get, you will have 3 lock activities. Well, 4. You have bucket lock, record lock, bucket unlock, record unlock eventually. And this halves that number of locks. And locks is the one serialization component. This is where everybody has to wait for you. And even if it's not the same lock, everybody has to go to the lock manager and wait for your little diddly thing. At priority level 0, you created a lock, but the guy at priority 258, I'm just making up a silly number, still has to wait for you because the lock manager is busy for you. Did you want that to happen? Possibly not. So I think for me, RMS tuning is lock tuning these days. IO tuning is fine. We have SSDs, everything works just fine. But lock management, how many locks per second can your system do? 100,000 locks per second? 200,000? I think that's about the max still the max these days, right? So if you need, your system will bottleneck at that point. Can't stress it enough. Global buffers, they work, efficient in memory, efficient in locks. So then you ask, of course, how many global buffers? Well, I don't know. Just a bunch. When I first made this presentation, well, the big thing is none is the wrong answer. We need some. Do not postpone to get it perfect. Just pick a number. Please, just pick a number. The limit was 32K, but actually you can go bigger these days. Practically, let's start out with something in the 200 to 2000 range. I used to say 42 is the answer to life, universe, and everything. And indeed, that number will work, but that was in 1990 when I first made this kind of presentation, and memory was still expensive then. Now, let's say 200 is the very bare minimum I would start at today. You want to, if you're concerned about memory, then maybe at least, because for every user process that uses the file, you save memory by going global, right? So you could, if you're really worried about memory still, then you could take the number of users into account. Really, you want to cache the indexes. That's what this is all about. The goal is a nice hit rate, right? We can monitor it with monitor/RMS/ cache or something like that. You can see what the hit rate is. And of course, we want 99.9% hit rate, right? But this is where sometimes it's good enough. So if I have 99% hit rate, but I'm doing 5,000 accesses a second, I'm still doing 50 IOs per second. And the 99 might not be good enough. And yet, when I have 90% hit rate on another file with just 50 accesses per second, I'm down to 5 IOs per second. And who cares whether the 5 becomes 4? Right? You feel that? So it's more about making an impact on the system. Locks, you'll get the presentation so you can see, you can read back on some of those details. Record locks, so global buffers managed to reduce the number of bucket locks. But still, as I described, in a shared environment, when I'm reading next, read next, read next, I will get a record lock, give the data back to the user, and the user will then probably say, give me the next record. I demote my record lock and get the record lock for the next record, and on and on and on. But I might never have had the intention to do anything with that record, and yet I will get a record lock. And there is a bit in RMS that says no lock. Yeah, well, fooled you. That means no lock held. But we will take out the lock to see if somebody was locking it and then give it back. So the only way to RMS saw it as an issue and saw that mostly from COBOL programs. They said, why am I locking if I'm not doing anything special? So they came up with a semi-solution where if you have, and COBOL did this, if you have the no-lock bit set and if you have regardless set, I forget, if you have both of them set, clearly you don't mean to have any locks, even though we're going to give you one, in those conditions, and you say the magic word and spin around twice in the system, then no query lock set system/no query lock. If you say all of that, then we will not do a lock. It ain't happening. Those locks are still happening. So we do have a great real solution, and that is the is it on the next slide? Whoops. NQL lock. So that was so also with version 7.2 we got a new bit in the RAB, and this NQL has been there for 3 decades now, and says no query lock, do not ever get a record lock if I have this condition set. But it's only a programming option, so many people cannot get there from here. There's no option in COBOL to do that. So for Andrea, I created a set of subroutines. COBOL has a RMS current RAB feature where you can inquire where the current RAB is, the internal control block. And so it's a trivial subroutine to get the current control block, set the bit, clear the bit, 2 subroutines, one to set, one to clear, and call it from COBOL. But if you see your application using way too much logs and you see log kernel time, you may want to actually dive into code at some point and see if you can set the no query log bit where that's appropriate. Yeah, that is, those are the big structural things. Understanding buffers and logs, understanding how the system accesses the data. I got a bunch of independent topics, and the one I am most dear to my heart. Do I have 5 minutes still? Or? Yeah. The one that's most dear to my heart because it has hurt most people out there is the duplicate key change. Shall I make the little anecdote? Yeah, we'll make the little anecdote, and we'll get there. Duplicate key change. We saw the alternate key. So if I have a record with, well, which is the best example? Well, let's just say print jobs, and they need to be printed and they're done being printed, right? So I have a record that goes in, and done has a pointer to a record that has already been printed. So that record points back to the data record that's behind it in the alternate key, and in that alternate key, I need the key value done. But because I have more than one key with the key value done, I build up an array of those RFAs, essentially. The 4-byte bucket number I talked about, the 2-byte ID I talked about, and a 1-byte flag to see. You always have to have a flag. Why not? I forget what the values of the flag are. Most of the values in the flags are actually for the for run unit journaling. There's a bunch of flags for that. But the big thing is that for every record, every print record that is done, there's a 7-byte addition to the key value of done to point to the data record which was done. So 7 bytes. If your bucket is 16 blocks, 8 kilobytes, that's 1,000 pointers, right? What if you have more than 1,000 print jobs done? And you will over time. Then we add the next bucket of doneness and the next bucket of doneness. And what we do when a record was not done and we change it to done, we promised that we will always add it to the end to keep the order of it was the last print job done can be found at the end of the list. The first print job that was done is the first one in the list, and we promise to maintain that order. So now RMS says, if you look carefully back in the structure, there is no pointer as such to do that. So RMS will know where to start reading. It reads the first bucket of done records, and it says, oh, there's no room to put the next one, and it goes to the next bucket, and the next, and the next, and the next. How deep do you think you can go with that? Real deep. So that's the arrival order. We insert, go at the end of the sitter chain. You can have a small bucket, 500 sitter records. The biggest bucket, 63 block, is only 5,000 RRVs. So if you have millions of duplicates, 1 million divided by 5,000 is 2,000. So now in a picture, we have these records done, and it keeps on going. And we might have 4 buckets of done and 1 bucket of active and 1 bucket of requested. But I hope I forget what I have a picture here. I want to go, this got slightly messed up, sorry about that. I got so tired of counting, I wrote a program to count them. Called a tune check, I call it sitter to begin with, and then it evolved into a more extensive program. And this is a real example. Live customer has a file like this, and the tune check reports how many duplicates for key value you have. And so it had 25 records that had key value 1, key value of this number. It has 46 at a key value of 29 something, and it has 1,750,000 records with the key value of 000, like I don't care value. Now, to store 1.75 million records, you need 4,000 buckets. So now if I add one more record with that value, Is that going to be likely? Add one more. Well, those millions of records had to come from somewhere, and they keep coming. So it's the most likely value to come into that file. It's happening over and over. I will do 4,000 reads to find out where to write. I'm sorry, that's how it works. There's ways to fix it, not today anymore. So that's how it works. And so 4,000 buckets being read to write one record. One is of magic, and I call it the $1 million bit. And why do I call it the $1 million bit? Because again, back in the 1990s, the customer complaining severely about performance, and overnight it went from being decent to being absurd. What was the problem? Let's exaggerate this, but they had set 4,000 global buffers on the file, right? And so we start reading this duplicate keychain and we read 4,000 buckets. And then we need to find room for bucket 4001. And so we toss out the first one. And so all the buffers that we build up during the first scan, when you insert one more record, oh, I just tossed out record 1. Let me find room. Let's toss out bucket 2 to make room for bucket 1, and I'm going to change my own. So overnight, as they went out of that cache, it was actually the storage cache they ran out of. They were ready to put $1 million to upgrade to SSD, so to speak, to make it work. And there's a bit in RMS that says, if all the key bytes have the same value, then don't bother making a key for it. So by setting that bit, that customer saved $1 million just by setting one bit it's a bit on the file, so they didn't need to have to change code for it. So that's the null value bit. You can specify what the value of the bit is. By default, is it not a space? I think it's just a binary 0, the default for it. But who cares? You pick the value that's appropriate for your application. And that, my friends, is the biggest thing, performance issue, is these duplicate keys, and in the slides you'll find how you can detect them. And in my tools, the RMS TuneTech tool, which I will have to give a link with my presentations for those tool set, and then you can there's some further indications on how to solve that. Right? That's all the time I have. I think 40 more slides. If you're interested in different issues, and I can talk to them if you buy me more beer.
I have a question then. So when you insert $1 million records, but you also delete them. And when there are no records in the file, it's very slow. So we have to convert every hour. Why does the RMS see that by themselves? No records anymore, I can reset everything.
So when you're reading, you're maintaining a file is being filled with records, and then you delete them and you reinsert, there's nothing left in the file. So it's kind of, I see that when you have queue files, you have things to do and you put a new record, and as you have done them, you delete them and you go on. And what is the observation you made? I didn't hear it quite.
Yeah, so I have to convert that file every hour to keep it fast.
Yeah.
But why doesn't the RMS see it themselves so the file is empty and reset all the points?
I already gave you a reason, and that is the ID. So we could run out of record numbers. In your case, you're never going to remember the RFA. There's no way to tell RMS that the RFA is irrelevant, so it keeps on insisting that it cannot reuse the number of the record in the bucket. That is one reason. Also, what I do see there is, if you have, and it happens a lot, when you have a work list to do, and normally there's only 5 elements in the work list, and delete them, you're done. But now it spikes to 20. So we allocate the next bucket to hold the other 5 records. And now when you delete that key range is still allocated to the first bucket. So that magic star that was in one of the first slides, and I get the pointer back, when I had a high value, the high value points to the end of the list. But as soon as you exceed the end of the list, it becomes a real value of the last record in that list. And we allocate a new bucket with a star by it. But now I have this emptiness. We should be able. I should be able to prompt to it. It doesn't matter. That's actually so. The good news is, I have 5 slides for this subject. Deleted key ranges, and how they come, and how you can detect them, and what the example, and what you can do about it, and potentially, you just need to increase your bucket size to 63 to have more flex in the storage area, not exceed into the next bucket. But we'll talk about details with specifics about your application. But this is often deleted key range is a recognized problem. RMS doesn't do anything about it because it's constrained by the promises it made.
It's fast again. Yeah. I convert all the time, and it goes fast.
Yes, it converts now. Yeah. I actually had, because for one of my earlier coding things was to not recreate a file, but just to overwrite the prologue to say you're empty and move on, which is no fair, but it works. Yeah.
We have to wrap up for the other people, but do you have an email address for additional questions? Do you have an email address for additional questions? Maybe
it was on the first slide.
Okay.
Email was on the first slide.
Okay.
Yes. So if you have additional questions, please email them at the first slide, and I will try to make sure to get my my tool set on a zip file together with this application, with this presentation, and I have a subsequent tiny presentation, a 20-minute at the end of the afternoon, if you're interested in a couple more things.